today is the 9th session of our lecture series, and we are grateful for Professor for conducting this lecture series. Actually, this has been a very interesting lecture series, and we have received many positive feedbacks from the participants, and also our video recordings in YouTube are having many views, and so that is also showing how important this lecture series is. So I would like to invite Professor to continue. Over to you, sir.
Okay, thank you, Bandhuka. Today we talk about torsion in beams.
Yes,
Everything
sir.
is okay, Bandhuka?
Yeah, we can hear you, sir, and we can see the screen as well.
Yeah, okay. Right. So today, now this is kind of a note that was taken. I have discussed this briefly, but I will repeat what we discussed last time. Torsion. Now, many of you would have learned torsion. Torsion is, we have a beam, then we beam and we subject it to the moment like this. And if you use right hand corkscrew rule, axis of the moment is this way, then you can get torsion. So you can get torsion. And I will show you a real situation where torsion can happen. Just 1 minute. This is a presentation I did some time ago. And right. Now we look at this particular building. Now you can see this is not a big building. It's only a 14-story building. Then you might ask why I show this. You can see the lower part of the building is a car park. And the upper part of the building is reserved for apartments. And at this particular level, you can see there's a transfer flow. So it consists of transfer beams and a top slab. Now, if you look at the right-hand side diagram, it's clearer. And you can clearly see it. Here you can see big beams when you compare with the other members. So these beams are 1.5 meters deep. Generally of square section, close to square, not rectangular. And we see why it is important. And we go little further down. Right. Now you can see the kind of situation that can arise in just under the transfer beams. And you can see this M33 diagram, this M22 diagram. Most of the time when you look at an output, generally we look at M33, but in this particular situation, I looked at M22 as well. Why? And if you look at the reason, you can see there's a column and then there's a beam going this way, and these beams are much larger than the column. So you can get a substantial moment in the column. And if you look at the column moments, at a lower level, they are much smaller than the column moment here. So you can see there's a possibility for us to get higher amount of reinforcement in the upper part of the column at a higher elevation just below the car park than at the ground level. So this is something that you might encounter in buildings with transfer floors. And you have to be little concerned about it, because otherwise, you might think, okay, what is most critical is at the bottom of the bottom, not here. But here you can see there's a big moment, much bigger than the moment here. Is that clear, Bandhuka?
Yes, that is clear, sir.
Yeah. So basically, when you are designing a column, just below the transfer plate or the transfer beams, you have to be very careful about biaxial bending situation. Biaxial bending, because they can be biaxial bending on the column, and generally we select the columns to be strong in one direction. But in this particular instance, you can see the column needs a huge strength in the other direction as well. So these are some of the concerns that you have to have. Now, and associated with the same transfer plate, now if you look at here, you can see the transfer plate, the transfer beams are here, and the edge of the transfer beam, what do you get? You get a wall. Now, generally, we expect to load a beam at the center. So, when you are applying a load on a beam, general expectation is that we'll apply the loads on the center of the beam. So, the beam will not be subjected to high torsional moments. But what has happened in this particular instance is, we have to extend the building to the very edge of the transfer beams. And because of that reason, you can see that the loads are not acting on the center line of the transfer beams, but they are acting on the edge. So let's see what are the repercussions of that. So we have a transfer beam, and as I told you, the transfer beams must be large, and they must be like this, something like this shape. And what is important? What is important is when it is subject to torsional moments, it should be able to resist it. And the problem is, if you want, you can have the beam loaded with some walls on the center line like this, but some other walls might come here and transfer the loads here. So if the loads are transferred at a place like that, what could happen? We'll get torsion. And this torsion is equilibrium torsion. And it is not compatibility torsion. Now let's see what is the difference between equilibrium torsion and compatibility torsion. Let's say we have a beam here, another beam here, supported, 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 supported. Now what happens? The bending moment on this beam could be a torsional moment on the other beam. But in this particular instance, if we say this is not torsional resistant, can the system exist? Yes, the system can exist. Then we say it's compatibility torsion, and what we do is we say torsional constant J or C close to 0 when you are doing the analysis. I can give you one example. Let's say take a beam bridge, I beams, what we call M beam bridge. Then there's a deck. Now to analyze the bridge, what we need? We need a grillage. Every 1 meter interval we'll have a grillage. These are 1 meter. We'll have members this way. So for each beam, you can apply a torsional value C. But what will happen if you apply that? Then when you analyze, you will find, because you have allocated the value C, now this is attracting more moment, and you need a bigger section to resist. So it goes on like that. You apply you assign a value, then it says, okay, I need a bigger value. So because of those reasons, we say, let's analyze it as a torsionless system. How to get a torsionless system? So once you analyze, you should get the answer for torsion as close to 0. For that, we have to say torsional constant of these beams is very low, going closer to 0. So what we do is we allow the program to calculate the torsional constant, then multiply it by something like 0.01. So we bring it down by 100. And what will happen? Not 100%, 100 times. What happens? Then we plot the torsional moment and we find it is very small. But what will happen? Because you have made the torsion 0, close to 0, you get a higher bending moment. So we'll be designing these beams for higher bending moment. So in the compatibility torsion situation, there's no risk of collapsing. There's no risk of cracking, even if we ignore torsion. And the compatibility torsion situation comes when you have beams in 2 different directions, and you have a beam or slab situation like this one in beam's case, where the members are unable to carry torsion, but they can remain flexible while having adequate flexural strength. So that is one situation. But if you, on the other hand, you have a beam connected to a cantilever. Beam is a long one. There's nothing to balance on this side. And when you apply load, the beam will be subject to twist. And that is not, so this is the situation. You have a beam subject with a cantilever, and the cantilever is loaded. So beam is subject to torsion. And there's nobody to balance it. So this is equilibrium. This is equilibrium torsion. And this is compatibility torsion. So you have to be little concerned and see whether you have equilibrium torsion or compatibility torsion. Bandhu, today's 8th lecture or 9th lecture?
Today's 9th lecture.
Yeah. 9 and page 1. Date is 31st. 2024. 1 month has already gone.
Yes.
Okay, yes. So let's see. Let's look at the note again. So it's very important for us to understand that there are 2 types of torsion. One is, see, this equilibrium torsion. We are applying a load where the beam is fixed here. And definitely you will get a torsional moment of W times C. Is that clear, Bandhuka?
Yeah, that is clear.
That's clear. But this is equilibrium torsion, because these beams are not going to fail. So you should be able to identify those 2 different scenarios. So that's the first thing we have to learn. So what happens when you have torsion in a beam? So it's twisting. And I'm not sure whether you have broken a piece of chalk. You take a piece of chalk, it's a brittle material, then you apply torsion to it. What happens? It cracks diagonally, like this. Cracks diagonally. So if it cracks diagonally, what shall we do? We have to provide reinforcement here, vertical reinforcement. But it's going to crack on this surface. That means we have to have reinforcement here. And it's going to crack on the other surface. So we need reinforcement like that. It's going to crack at the bottom. So we need additional reinforcement. So what is this? What is the meaning? Okay, we need a special shape of a link. So we have the beam like this. It is going to crack here, crack here, crack here, crack here. So we cannot have a link like this. This is wrong. This is not a torsional link. This is a shear link. So if you want to resist torsion, we need a special link. A cross link like that. Is that clear, Bandhuga?
Yes, clear, sir.
So this is a torsional link. This shear link. So any beam subject to torsion, we'll need this type of links. So this is something that you have to be very careful. But sometimes, you get people who think they know everything at the sites. And even when you draw this, they might put this. So you have to educate them. Saying that torsional link is different. These are an element subject to torsion. So that's an additional information. And I'll share this screen again. And here now you can clearly see the problem. Here you can clearly see the problem. Here you can clearly see the problem. What is the problem? None of these beams are loaded axially. The loads are acting with an eccentricity. So they must be subject to torsion. And how to create that situation? Can you see some rigid arms here? A rigid arm here? Can you see a rigid arm? Banduk, is it clear?
We can hear, sir. We can
you can clearly
see that.
see this one.
Yeah.
Here you can again very clearly see a rigid arm. So when you are analyzing, you place the beam at its center line, you place the wall at its correct location, and if they are not coinciding, you will connect them with rigid arms. So it's a rigid arm can be a section as large as the transfer beam. Rigid arm can be a section as large as a transfer beam, or otherwise you will select a beam like 600 by 400 as the rigid arm, but you will go to the set modifiers and multiply it by, go and multiply the I value by, say, 1000. I value can be multiplied by 1000. Then it will become a rigid arm. So if you are using the same section as I, so as the transfer beam, then you have to have two different materials. For this one, you should have a material without mass or density. Why? It is a fictitious beam, not the actual beam. There's no actual beam like this. It's a beam that we apply. So unless you use zero mass, zero weight, what will happen? All these extra members will add weight and mass to the structure, which is wrong. So anything not there, what shall we do? We'll say the mass is almost close to zero. Weight is almost close to zero when we define the material on the computer program. On the software, we have to define the material. So define a different material. Transfer plate, transfer beam, zero density. Transfer beam normal, transfer beam zero density. So do two different materials. Property wise the same, except the weight, because now in the model we are adding additional members. So what is the meaning of the model? Model is not the actual structure. Model actually represent the behavior of the structure. So these are mathematical models that we have created to represent the behavior of the structure. So don't get confused that, in the case of architects, when they are generating a 3D view, they must generate what it actually looks like. But for the engineers, what matters is the behavior. What matters is the behavior. So what shall we do? We must represent the correct behavior, not the correct shape. So in that context, we have to make sure we don't add additional masses and additional weight just because we are going to create a mathematical model with extra members. This is a mathematical model with extra members. Because in the actual structure, member is so large, we can support the wall directly on the member. But on the model, the width of the lines is almost zero, so we can't give any width to the large members. So we have to artificially create that width, and when we artificially create the width, we have to be very careful with the mass and density. The moment you give the actual values of normal concrete, you will be adding extra masses and extra weight at those locations. So we have to define a special concrete for it. Is that clear, Bandhuga?
Yeah, that is clear, sir.
That's clear, right? Okay. So that's the other important thing. And here you can see, now it's a very clear diagram. So these members are not where you think. They are all located with an eccentricity, and here you can clearly see that this particular wall will definitely cause some torsion in this particular beam. So that is something that we have to look at, and also here you can see the torsional moment diagram. So here you can see how the torsional moments will be coming. So that is also given. Right. So I'll stop share on that. Right. So now I'll share the note. The moment you look at the diagram, you can see why we need cross links, because torsion is everywhere. So you can't have any weak corner. So in the shear link, where we lap is a weak corner. But for torsion, we can't do any of those things. So that's why we go for the close link. Now, when there's torsion in a box beam, just one moment, I'll come show the screen, the white sheet to you. I'm just drawing the diagram just to get the information. Q is equal to tau I Ti equal to T over 2AK. Okay, so I'll stop sharing. So that particular equation you have seen just before, the same equation I have written here, is applicable. It's applicable to sections like this, hollow sections. Now, what is the advantage of hollow sections? They are torsionally very stiff. Torsionally, they are very stiff. Why? Because we have a big section. And let's compare it with an I section. What happens when it is subject to torsion? We'll get a torsional shear flow going around the sections. This goes this way, this goes this way. But what is the lever arm? Very small. Now here, how the torsional shear occurs. Like that. So, if the torsional stress is tau I, then you have to multiply it by the thickness. Then you will get the force. Tau I, Ti will give the force. And what the theory says is, this force, we call it Q, is equal to torsional moment divided by this line demarcated area. What is this line? This T. What is this one? T by 2. So you take half the width, take half the width, take half the width, and then we take the area inside that, and this area is 80. So we have an equation like this. And we can find the torsional stress. So if you have a section rectangular shape, what will happen? The torsional shear will flow like this. But here the lever arm is small, here the lever arm is big. So what will happen? The efficiency will be governed by this particular one, not by the big one. So though for beams in flexure, this is good. For beams subject to torsion, this shape is good. Square is good. Why? Because we know then for all sides we maintain the same size. Now, what happens when you try to analyze a section like this? The Eurocode says, or don't analyze it this way. Find something that will give your equivalent hollow section. So this is the equivalent hollow section. So what you do is you will calculate we do the calculations considering that this rectangular section or the square section is not going to be a solid section. Why? If it is solid section, what is the effectiveness of this to the torsion? Very low. What is the effectiveness of this against torsion? Very high. So there is no point in bothering with the inner part of the section. There is no point in bothering with the inner part of the section. Let's look at the outer part of the section. So what we do is we define an equivalent section. We define an equivalent section whenever we want to calculate the torsional requirements. Is that clear, Bandukha?
Yes, clear, sir.
Right. So this is number 2. Then we have to see how we look at torsion. So I'll share the screen again. So this equation I showed you, and I told you that for hollow sections, this is very useful equation. And now you can see how we make hollow sections in a rectangular or square beam. Shows elastic stress distribution in a solid rectangular section subjected to a torsional moment. The shear stress due to torsion are tangential to the sides, and in an elastic material, the maximum shear stress occurs in the middle of the longer side of the rectangular section. The stress is zero at the centroid of the section and increases in a nonlinear manner towards the edge. A very high portion of the torsional resistance comes from the shear stresses acting over a short thickness near the surface of the box. Therefore, for all practical purposes, the solid section can be treated as a thin walled section, hollow section. So you can see the thin wall hollow section. For all our practical purposes, we consider it as a hollow section. Why? Most of the torsional moments acting on the section will be resisted by the outer skin. Now, when you are calculating this thin section, again it says is taken as AOU, but should not be taken as less than twice the distance between edge and the center line of the longitudinal reinforcement. So what it says is, I'll stop share. When you have a rectangular section or a square section, here we provide reinforcement. And we have links. And then we define a thickness for the section. What it says is, if this is simply the minimum thickness of a section should be 2A. Even if the calculation gives a lesser value, you must go for 2A. That is the meaning of that. So there's a minimum thickness for the wall based on the way that you have arranged the reinforcement. Sorry, sharing the wrong plot. Then how do we find the thickness? The effective thickness is considered as A divided by U. U is the outer circumference of the cross section. A is the total area of the cross section within the outer circumference, including the inner hollow areas. So there's a procedure for finding the thickness of the wall, but we'll look at the example and find it so it's easier to understand. Now you can see how the torsional flow occurs. Torsional flow occurs like this, and you can see T effective should be minimum of twice this value. So that is the T effective. Then one of the things about torsion is because torsion goes right round. Providing the link alone is not sufficient. Providing the link alone is not sufficient. So we need extra longitudinal reinforcement as well. So why? Because these stresses are inclined. So inclined stresses can give rise to additional torsion, additional longitudinal forces. So you get an equation like this in the code. Equation 628. That tells you how to calculate the longitudinal reinforcement. Then the code tells you we can't have any moment carried by torsion because there's shear as well. So we must satisfy this particular condition. T ED is the applied torsional moment. TRD max is the maximum torsional moment of a section. And VED is the applied shear force. And VRD max is the maximum shear that it can carry. So last time I showed you how to calculate VRD max based on the shear angle. And when this is subjected to torsion, generally we try to keep the shear less. So what is the meaning of that? How to keep the shear less? Flexural shear less. Because we go for square sections. The moment you go for square sections, you'll find torsion, flexural shear drops, and torsional shear also will drop, and we have a chance of satisfying this particular condition. Now these are long equations, and the ideal way is to show you how to do the calculation with the example. And DRD max, again the equation is given. So what you do is, first you do the shear calculation and find the theta value. And use the same theta value for torsional calculation as well. Right? So what you do is, you will first do the calculation and find the theta value for torsion. And I told you, when we select a big section, what is the theta value for shear? Flexural shear, the theta value is 22 degrees. So we can substitute same angle. So whatever the angle is the same as that you use for flexural shear. So you can see this is the actual moment acting. This is the maximum moment, no problem. This is the actual shear acting. This is the maximum shear. For this also, we last lecture we learned the equation for this. So which means there is no problem. We can see whether this condition is satisfied. So what is the first condition to be satisfied? This condition. If you are not satisfied in this condition, there is no point in finding reinforcement. Why? The beam is going to fail in shear. So we have to be careful. The first thing is, first define the hollow section. First convert the rectangular section or the square section to a section like this, hollow section. What is the second step? Check this. And once you check this, you can find other reinforcement as well. So that's how it goes. And then in the case of open section, there's something called warping torsion, but generally these days we can easily take precautions against warping torsion. So I will not worry too much about it, because for closed thin wall sections in solid section, warping torsion may normally be ignored. So basically, that is something that we ignore. For rectangular sections, solid sections, solid square sections, and also hollow sections, you can ignore it. So you don't have to worry, as long as they are closed. Then we look at the design example. So I'll use the design example from Musli and Banji's book, because it's a good example. It tells us a lot of information. the example. And just one moment. Right. Okay. So we look at this particular example. Now, if I am to explain how to do this torsional calculation, the first thing is I need a beam. So we'll take this particular beam, span is 6 meters, subjected to a permanent load of 60 kilonewton meters and variable load of 18 kilonewton meters. The characteristic strength of concrete is 30 megapascal. Characteristic strength of steel is 500 megapascal. And the effective depth is 540 millimeters and the breadth of the beam is 300 millimeters. So you can see this is a typical situation. And first thing is to see how to design the beam. And then we have to see how to provide the torsional reinforcement if it is subjected to torsion, right? So the first thing is I must design this beam, right? I must design this beam. So for that, now I'm going to explain how to calculate the torsional shear link requirement by using an example. Because if you look at the code, okay, I forgot to look at the code also. I show you the equations given in the code. So this way the torsion starts 6.3. It says general. Then it says the design procedure. You are now familiar with this particular equation. And torsional shear force is can be calculated by using this expression. And then it says the required cross-sectional area of longitudinal reinforcement of a torsional ASL may be calculated from the expression ASL over YED sigma over UK, that is the perimeter of the area AK, and it is given by an equation like this. So sigma ASL is, these may be different, so we have to go for addition. So I'll show you how do you make use of this equation to find the amount of longitudinal reinforcement needed. And then it says, you have to fulfill this particular requirement. What is the requirement? That is to make sure the torsion and shear once combined are not excessive. So that is also another condition. And then it comes to the warping torsion, which is not applicable to us. So torsion is only that much. Not a great deal of information. Only a little bit of information. So that's why you have to look at the textbook. Because the code is not very helpful, only few equations. It covers it. So we have to look at the textbook. Okay, so that's a part given in the code. Is that clear, Mandukar?
Yeah, clear. Yes, sir.
So this is little different approach because you have to go with an example. So what you do is you go with an example, then write a spreadsheet, and then let the spreadsheet do the calculations because the code is not very helpful in the torsion. Right. So now I will share the note. Right. So before we design for torsion, let's design the beam. Now, if you look at the beam, the length is 6 meters. Subjected to a load of 60, permanent load 60 kilonewtons per meter. the imposed load of 18 kilonewtons per meter, and then, so what is the bending moment? The total load is 60 into 1.35 plus 18 into 1.5. Mandu, can you find the value? 60 into 1.35 plus 18 into 1.5. What is the answer? 60 into 1.35 plus 18 into 1.5.
108.
180
8.
kilonewtons per meter. 180, is that right?
108.
108, all right, 108. Then you can get WL squared over 8. That is 108 into 6 squared divided by 8. 108 multiplied by 6 squared divided by 8.
486.
486 kilonewton meters. If you find MOBD squared, that is 486 into 10 to the power 6 divided by breadth is 300 millimeters and depth is 540 millimeters squared. What is the MOBD squared value, please? 486 into
3000 exactly.
No. 486 into 10 to the power 6 divided by 300 divided by 540 squared.
Squared, yeah. 5.56.
5.56. So it is actually a doubly reinforced beam. So we'll consider that, whatever the reinforcement given here is okay, correct. So the reinforcement selected is 2H32 plus 2H25, and for the compression reinforcement 2H16. And 2H25 is curtailed, 2H32 goes to the very end. Okay. So that's the reinforcement arrangement. And if you look at the shear reinforcement for the beam, the shear force is WLO2, that is 108 into 6 divided by 2. What is the value, Bandhu? 108 multiplied by 6 divided by 2.
324.
324. And then 324 is the value, but we have to consider the shear force at the face of the support. Shear force at the face of the support. Shear force at the face of the support, how much is it? I think it comes to 308. So it is 324 multiplied by the width of the support is 300 millimeters. So you get 2850 divided by 3000. 324 multiplied by 2850 divided by 3000. What is the value? 324 multiplied by 2850 divided by 3000.
307.8.
Yeah, so 308. So you can see these values are okay. 308 at the face of the column. And then they are found where the nominal links are needed. So this area nominal links, this area design links. Got it?
Yes.
Is it clear, Bandhu?
Yeah, that is clear.
Right? That's clear. So that's what we learned last time. So now we have a beam having shear links. So you can see we know the longitudinal reinforcement, we know the shear strength. Now let's assume that this beam, due to some reason or caused by loading, is subjected to a bending moment. sorry, not to a bending moment, to a torsional moment of 24 kilonewton meters. Torsional reinforcement is to be designed for the beam of this example, which is also subjected to an ultimate torsional moment of 24 kilonewton meters. In addition to the normally distributed load of 108 kilonewton per meter, already considered in the previous example, right? So basically, we have a beam like this, subjected to. So what is the first step? Now we have a solid section. We have to find the equivalent hollow section. We have solid section. We have to find the equivalent hollow section. So first part is that. Right. First part is finding the equivalent hollow section. Number 3. So how do we find the equivalent hollow section? So you can see some additional information. VD is 308 because we need the VRD max. Can you remember we have to use this particular equation? Right. So for that we have to calculate few things. And when you look at how to find the hollow section, what it says is the thickness of the box section is equal to A divided by U. A divided by U. So we have to find what is U, what is A. What is A? A is 600 by 300. This is 600, this is 300. So what is the A is the total area of the section. So A is 300 multiplied by 600. What is U? U is the perimeter of the section. Perimeter of the section. So what is U? U is the perimeter of the section. That is twice 600 plus 300. And when you do this calculation, you will find that the answer is 100 millimeters. So what has happened? What has happened? So I'll stop here. So we have a 300 by 600 section. 300 by 600 section. And we have converted it to a section like this. 100 wide. 100 wide. And here also 100 wide. 100 wide. And this is now going to carry torsion. Doing what? Generating a torsional shear stress that goes around its perimeter. Like that. Is that clear, Mandukar?
Yeah, clear, sir.
Yeah. So what you have to keep in mind is this procedure is little different to the procedure given in BS 8.10. In BS 8.10 for torsion, it does not consider a equivalent section. It simply considers the total section and it gives a procedure. But in this one, it is more logical. Why? Because center of the beam is not doing anything. So we need not include the center of the beam in our calculations. So we ignore it. That is the process. Now we have to see. So I'll share the screen again. Okay, so now we know the size. Then if you look at the equations, for TRD max, we have AK and TED. So effective thickness and AK. So what we do is we will calculate those values. So we calculate those values. So area of concrete AK is from the perimeter, and so if I stop share, AK is this area, and that area is B minus T effective, H minus T effective. So B is 300, H is 600. So that is 200 multiplied by 500. That's 200 multiplied by 500. So I'll share the screen again. You can see the value 100 into 10 to the power 3 millimeters squared. And you can calculate the perimeter also. Perimeter is 1400 millimeters. So we have that. Now what is our next task? Our next task is we have to see whether this torsion is excessive based on the shear already available. So we have to go for this equation TED or TRD max plus VED or VRD max, and we have to make sure it's less than 1. So what we have done so far is we have not done any shear calculation, torsional shear calculation. We have done the direct shear calculation, but we have not done any torsional shear calculation. And what we are going to do is we are going to see whether the torsion is excessive or not. If the torsion is excessive, we will have to go for a larger section. But if the torsion is manageable, we can stick with the current section. So we are going to see what's happening. So the first step is see whether torsion is excessive or not. Now for this we need VRD max. Now how do we find VRD max? So I'll stop share and I'll share the code. Now we are in torsion, but if we go to shear, direct shear, we have the equation for VRD max. And so that means VRD max can be calculated. VRD max is alpha CW, and we know alpha CW is 1. So here it says alpha CW is 1 for non-pre section. So that is 1.0 multiplied by width of the web 300 multiplied by Z.9 times 540 multiplied by nu. Nu is a capacity reduction factor, multiplied by 30 divided by 1.5 divided by cot theta plus tan theta. So I told you the first step is assume theta as 22 and then substitute in the equation. And so Bandhuka, shall we do this calculation with the first we will have to calculate this new value. New value is just one moment. I'll show the equation for new value. New value is 0.6 1 minus FCK divided by 250. Bandhuka, shall we calculate the new value first?
Okay, so I can't see the paper.
No, you don't have to see the paper. You can see the equation here. 0.6 times 1 minus FCK or 250.
Okay.
FCK is 30. This equation.
0.528.
0.528. Okay. Now show the paper. Right. So I will go to the equation. VRD max. Right. So this is the equation. Alpha is 1. BW is 300. Mandu, can you take down? BW is 300. Z1 is 0.9 times 540. Can you remember Z is 0.90?
0.9
Can you
times
see?
500. Okay.
Yeah. Right. 540.
Okay.
0.9 times 540.
Okay.
Nu is 0.528.
Okay.
FCD is design strength of concrete. That is FCK divided by 1.5. That is 30 divided by 1.5.
Okay. Then it is
Divide the whole
divided.
thing by cot 22 plus tan 22. Cot 22 plus tan 22. What is the value you get? Into 10 to the power minus 3.
534.76.
Yeah, VRD max is
34.76.
So shall we say 535?
Yeah. Okay.
And the design shear force was 308. Can you remember we earlier calculated 308?
308. Yes.
Yeah. So VED is the design shear force. If you look at the definition, VED is the design shear force, and just one moment. So this is the maximum, and the design shear force is VED, that is 308, right? So we have two values, 308 and 535. So we look at the note. So this equation. So we know VED, we do know VRD max. So VED is less than VRD max. So what is the angle then? Angle is 22. Angle is 22. Can you understand it, Bandhuga?
Yeah. Yes, sir.
Right? So angle is 22. And can you remember last time I said always select the section large enough so that angle will remain 22?
Yes, sir.
Yeah. That is easy. Otherwise, this becomes a little too complicated. Right. Then it says TED is known. It says 24. The problem. What is TRD max? Is equal to twice nu. And nu is calculated as 0.528 multiplied by FCW 1.0, alpha CW 1.0 multiplied by AK. Can you remember we calculated the area 100 into 10 to the power minus 3? 100 into 10 to the power 3.
Yes.
Multiplied by the thickness. Thickness is 100. Multiplied by sine 22 cos 22. What is the value you get?
Three 3.66 in 10 to the power 6.
Sorry? No.
3.66 in
No, I
10
think
to the power
we
6.
have missed something. We have missed something. Yeah, just one moment.
Okay.
FCD we have not multiplied. Right? So multiply that by 30 divided by 1.5. Can you remember? I have missed FCD.
Yes.
30 divided by 1.5.
Then it is 73.4.
Yeah, 73 point.
73.35.
Yeah, so you can see the answer that is given in the example is 72.6. Is that clear? So
Yes.
it's pretty close, huh? Right?
Yes.
So the equation given in the note is little different. And how do you know how to get this equation from the original equation? Original equation is given in the code. It says TRD max is equal to 2 nu alpha CW FCD AK T effective sin theta cos theta. And we know sin theta cos theta is equal to 1 over tan theta plus cot theta. Okay. Sin theta cos theta is equal to 1 over tan theta plus cot theta. Then, so I can, now the equation that is used in the note is this one. This may be easier. If you are writing a computer program, this equation may be easier. So we see how to get that equation. So TRD max is equal to, so I'll stop here. TRD max is equal to,
We got the value 73.4.
yeah, 2. No, I'm just trying to show how to get that equation that is given in the note. Because if you are writing a computer program, that equation is easier.
Yes.
Now you can see definitely you will write a computer program for this. Why? It's little too complicated to think and do. So this is the type of thing. It's very ideal for computer program. So because the procedure is set, so we can easily write it, and then you get alpha 2 nu into FCK divided by 1.5 multiplied by AK T tan theta plus cot theta. So 2 divided by 1.5 is 1.33. Nu F CK AK T tan theta plus cot theta. Is that clear, Bandhuga? This
Yes,
equation,
clear.
okay?
Yes.
Right? And if you look at the equation given that we have, that it is used, that's used in the design example, can you see? Same equation. Is it clear, Bandhuga?
Yes, yes, sir. Same equation.
So if you are writing a computer program, this equation is easy rather than writing the code equation. Do you agree?
Yes, sir. Agree.
Yeah.
That one
And
was
you can
difficult.
you also your value 0.528. So this TRD max comes close to 73.
Yes.
So now we can substitute and see whether it's less than 1. So what will you do if it is more than 1? Increase the width of the section. Don't increase the depth of the section, increase the width of the section. What will happen? Torsional capacity will increase, shear capacity will also increase. Then you can bring it inside one. Is that clear?
Yes, sir. Clear.
Because sometimes when you do this calculation, you will find it is more than one. That means the section is going to fail. There is no point in providing reinforcement if the section cannot take it. So, what is the best way to improve it? Increase the depth or increase the width? Increase the width.
Width.
Why? Torsion is, to resist torsion, square section is better. Rectangular section is poor. So we have a rectangular section, move it towards the square section, then the torsion will be okay. Got it?
Yes, sir. Got it.
Right, good. So that's what I wanted to highlight. Okay. So that's a check you have to make. Or shall we continue the remaining part of the question next time?
Yes, better, sir.
But otherwise, if I start, I might run way beyond 8:30.
Yes, sir.
Right?
Thank you,
So, what are the important things that we can summarize? Because one thing is clear, generally you never get torsion. But in the case of transfer beams, you can get torsion. Then you have to do a careful calculation. Calculation is straightforward, but it involves several steps. So if the calculation is complicated, but calculation is straightforward, but involves a number of steps, what is the best tool? Write a spreadsheet program. Write a spreadsheet. Like Excel spreadsheet, Excel sheet, you plug in the numbers, you will get the answers. But you have to have very clearly to see whether this less than one condition is met. Do you agree with me, Bandhuka?
Yes, sir.
The ideal, because these are still long process. Because we are not good in long process. Why? Because we make mistakes. When the processes are long, we tend to make mistakes. So when the processes are long, it's always better to computerize it. Use the computer with a well-written program so that repetitive calculations are performed by the computer, not by us. Computer is best for repetitive calculations. So these are repetitive calculations. So if you are designing a transfer flow, there will be many beams where you have to check for torsion. So I think we checked over 15 sections for torsion, but we did it for BS code because it's much easier to check it. But again, I did not I did not do the calculations manually. I did all the calculations using a program, computer program. Okay.
Okay, sir.
So so if you look at the note, if I go to the earlier part of the note, you can see we are having a situation like this. That's how the torsion comes. And that is equilibrium torsion. We must resist it by providing torsional reinforcement. On the other hand, we can get a situation like this. It's compatibility torsion. And we don't have to worry too much about it. Why? You can analyze this as a torsionless system and ensure that all the extra torsion is now converted to a bending moment. So this is not a major problem, but this is a major problem. And this you encounter in bridges, grillage analysis, we easily handle it by using set modifiers and assigning a very low torsional constant. But here we get a real situation. Beam will definitely crack here because we are twisting the beam. Concrete is a very weak material in tension, so it's definitely going to crack. What are you going to do? Make sure we have close links. And I showed the shape of the link, the close link, and you must provide that type of links. And when you do the calculation, what is the result? If the torsional moments are high, what would be the diameter of the link? You can easily get 25 millimeter links or 20 millimeter links at 100 millimeter centers. So that's the type of reinforcement that you need to resist torsion. So you can see torsion is a problem. If we can avoid torsion, we should avoid it. If we can't avoid torsion, then we must provide reinforcement to resist it. That's how it goes. Is that philosophy very clear?
Yes,
Try
that
and
is clear.
avoid torsion. Try and make the loads axial with the center line, coincide with the center line. But some situations like transfer beams, we can't do that. Then in such situations, we have to resist it. But there's another way actually to make it coincide. And if you look at this particular building, sometimes what the architect can do is, architect can bring the transfer plate, this because generally there will be less restrictions below the if the land is large enough, there are less restrictions on the area below the or within the car park. What you can do is you can bring it out. The center line can be brought out, and then the transfer beams will be shown as a band projecting out of the building. That is one possibility. Then you might be able to bring most of the beams in line with the walls above. So that's a one possibility, but not always, because sometimes in the restricted sites you can't do that. But in a site which is large, that may be one of the solutions to avoid torsion, because the moment you get torsion, you will need a lot of reinforcement. The beam can become very expensive. So to reduce the cost, one of the options is to project the transfer beam out and consider it as a kind of a band, visible band when you look at the building from outside. So that's one possibility. But in this particular building, they wanted it flush, so we had no other option, and we actually got 25 millimeter bars at 100 millimeter centers in certain locations. The huge amount of reinforcement, but unfortunately you can't avoid it. You can't avoid it. Is that clear, Bandhuka?
Yes, that is clear, sir.
So torsion is not a joke. Torsion is a problem, and solving the torsional problem is also very expensive. So that's what you have to keep in mind. Right? That's why I thought we should, although it's a little difficult, we should handle it, because it's very important for engineers to be aware that torsion can occur, and when torsion occurs, the repercussions can be very bad, because beams are going to crack right round, ugly cracking, durability problems. So we should try our best to either make the loads aligned so that we don't get torsion. On the other hand, we can't do it due to various site restrictions and the restrictions imposed by architects. We can't do it. We have to tell the client, you are making it very expensive by having these not coinciding, and you must try your best to make them as aligned as possible. Is that clear?
Yes, sir.
Right. So, are there any questions, Bandhuka?
Yes, sir. There's one question regarding this modeling. Isn't
Yeah.
it better have shell element drawn to the length of wall as a rigid arm, because rigid beam may induce excessive torsion moment on main beam?
No. Actually, what is the question again? Read it again.
Isn't it better have shell element drawn to the length of wall as a rigid arm, because rigid beam may induce excessive torsional moment on main beam?
No. Actually, you can't connect Shell element, you can't use a shell element to represent the
Link.
the question is whether a shell element can be used or a beam element should be used. Is that right?
He's asking whether shell element can be used for the rigid arm.
Generally, rigid arm should be beams. If you look at textbooks, what is recommended to form a rigid arm is always a beam. You cannot find anywhere in a textbook where they say, use a shell element and create a rigid arm. Is that clear?
Okay, sir. Yes. Yes.
So always, if you look at the standard textbooks, they always recommend use a beam and create a rigid arm. There's a reason for that also, because rigid arm technology came at a time when shell elements were not available on software, right? So the only option was is beam, but sometimes shell element also might work. But if you look at the standard textbooks, they all recommend the use of beam element as a rigid arm. Okay?
Okay,
Have I
sir.
answered the question? Yeah.
Yes, yes.
But if somebody wants, they can do an experiment and see whether it works. But generally, there's no harm in using rigid arm out of beams, because that's not recommended in textbooks.
Okay, sir.
Right? Textbooks going deep into the theories, they recommend beams. I have never seen a place where they have recommended shell elements to use to represent the rigid arm. Okay.
Okay, sir.
Right.
And there's one more question.
Yeah.
For a long off-center wall, at which intervals rigid links should be projected out from the structural beam?
No. You don't do that because wherever there's a wall. What he says is there's a very long wall.
Very long wall, and how many rigid links should be
Then
there
in that
like that?
in that case, you must not. If the wall is very long, that means you are having very heavy load on the transfer beam. Then you must one way or the other bring it to the center. Now what happens is we have several walls. You try to put some on the middle, but when you put some on the middle, some may not be on the middle. But if you have a very long wall, don't put it eccentric. That is a wrong concept. What do you think, Manduk? I mean, we have a very long wall. I mean, why can't we make it as coinciding with the center line? Because you have to adjust the beam. But what happens is you have a number of walls, right? Some are on the center line, some are not on the center line. Then you need a rigid arm, right? But if it is a very long wall, don't put it on as an eccentric wall. Always negotiate with the architect and make it a coinciding wall, with the wall coinciding with the center line. Okay?
Okay, sir. Okay, yes.
Yeah.
And last question: how to provide torsion in cantilever beam?
A torsion in cantilever beam is not a problem at all, because that it's a statically determinate system when it is a cantilever. So you straight away know the torsion. So when you know the torsion, design the reinforcement in the normal way.
And there's a request.
Is that clear, Mandugopi? Because if it is cantilever and the eccentric load is a statically determinate system.
Yes, sir.
Then you know the torsional moment at the place where the cantilever starts. What do you have to do? Just design for that torsional moment.
Yes.
Then the procedure is the same as this one. So we have to make sure there's torsional moment is less than this combined shear and torsion is less than 1. And then design the longitudinal reinforcement and torsional reinforcement in the normal way.
Okay. And
anything else?
There's a request. Shall we have a special session for village analysis?
Actually, we I showed it during the last year's session.
Sorry, sir.
Last year, when we're talking about figures,
Yes.
didn't we? I mean, that lecture may be on. Lecture may be available.
Yes, sir. I will get that lecture and will share the link in the group.
Yes,
It was
you
there.
better do that. But if there's any specific question, if the question can be sent to us, we can answer it.
Yes.
Right?
Yeah. And also participants, for you can send your questions to our WhatsApp group. We will have more idea about what is your question.
Yes.
And many questions coming. Is it possible
Any other
to have?
questions?
Is it possible to have secondary beams to reduce torsion?
No, actually, secondary beams. Now, generally, when you analyze the structure as 3D, you don't get torsion. Okay? Because torsional moments are so small, we ignore them. That's a compatibility torsion situation. But torsion comes only in this very special situation, that is the transfer plate. No other place. So you don't, when you are having secondary beams, all those things, you don't have to worry about torsion. Now, you worry about torsion only at one place. Worry that. Either you have a cantilever projecting out from a beam and exerting the moment, or else a big beam like a transfer beam where the loads are not on the center. That's the only situation. But be aware that you have to be concerned. You should have trained your eye to identify compatibility torsion and equilibrium torsion. Right? Anything that can be represented as a grid edge is compatibility torsion. So in the secondary beams, you can't get torsion because it's a compatibility torsion system. Whereas when you have a transfer beam with eccentrically loaded wall, it's a equilibrium torsion system. So equilibrium torsion situation must be provided for. Is that clear, Bandhu?
Yes, sir. That is great.
That's clear. So you must train your eye as a good engineers can straight away say whether the torsion is equilibrium torsion or compatibility torsion. Anything in a grid like secondary beams in a grid, it's compatibility torsion. You don't have to worry about torsion. Okay?
Okay, sir.
Yeah. Now, if you are an expert engineer, you should train your eye. Whenever you see a situation, the moment you see a relay, like in secondary beam system in two different directions, then it's not a problem. You can just analyze it as if in the without worrying about torsion. Whereas on the other hand, you get a situation where anyway when we are analyzing secondary beams, we introduce pin ends at the ends, pin supports.
Yes.
Where the secondary beam is connected to the main beam, we put a pin. So always secondary beams will be in simply supported mode. And how we achieve that in practice is we provide only two numbers of 12 millimeter bars at the top of the secondary beam. Moment you do that, all the second beams are simply supported, so no torsion will be transferred to the main beams. Is that clear?
Yes, that is clear.
Right. Okay.
Okay, sir.
Okay, then we'll wind up.
Yes.
So we'll continue the example next time, but my recommendation is you'd better write a spreadsheet. So whenever you get a serious equilibrium torsion problem, how to minimize errors is, because this is a long procedure, how to minimize errors is write a computer program. Otherwise, you are bound to make mistakes because this is too long not to make mistakes. So you can remember, I always show shortcut methods. Why? Shortcut methods, you can't make mistakes.
Yes.
When the calculations are long, you can make mistakes. Would you agree, Bandhu?
Yes, that is correct, sir.
Yeah. So anything long, computerize it.
No.
Anything short, don't computerize it, because sometimes before you enter the values on the computer, you can get the answer on calculator.
Yes, sir.
So if it is short, use a calculator. The long, computer. That's how we have to do it. Okay?
Yes, sir. Okay, sir.
Yeah. Okay then.
Okay,
Right.
sir.
So we'll wind up.
Okay, sir. Thank you very much, sir, for conducting this lecture series. Actually, by attending this lecture series, we are day by day improving our analytical skills as well as calculation skills. So thank you very much, sir, for bringing them out and uplifting the knowledge of practicing engineers. Thank you very much, sir, for that. And also, I would like to thank the chairman, Civil Engineering Sectional Committee, and Engineer Mangala Silva for continuing this lecture series for this year as well. And also, I would like to thank the ISL Secretariat, Publicity Department, and the IT team for their hosting arrangements. And also for all the participants, thank you very much for your participation. We really appreciate that. And thanks for your questions and enthusiasm. We hope that to be continued in upcoming lectures as well. And also, I would like to request from you to share our lecture series among your colleagues and interested parties. And also, we are uploading all these lecture series and recordings and study materials, so anyone can refer it later as well. Anyway, we appreciate your participation for this online session as well. Thank you very much. And we will see next Wednesday, 7 p.m.
Okay,
Thank you, sir.
yes. Thank you very much. Thank you.
Thank you, sir.